Okay. Hello. No. Hello. Yeah, I'm here to talk about stir again. I've talked about this 2 weeks ago, and yeah, here I am. So what I will be doing here is we'll go through the entire flow of stir. I'll be doing the proof part first. So beautiful diagram here, not done by me, but pretty. Let's go through the entire proving flow. So it starts off, again, I'm going to go through this while actually looking at the paper. So if you have your paper on your laptop, we can do that. You can just follow along. So first of all, the entire proving step starts from sampling folding randomness. So for the sake of a demo and for the sake of understanding, let's just set some value m to 2. This is actually the number of rounds. So number of rounds, in this case, it's just 1, 2, I guess. Yeah, and this is m, essentially, right? So yeah, let's set the number of rounds to 2, and let's set the folding factor to 4, in this case, just for the sake of demoing and showing the code later. So first of all, we start off by sampling a folding randomness. The verifier actually sends over rfold in this case, and with this, the prover can then now perform folding. So on the first round, so on I equals 0, actually this is incorrect. Sorry. Okay. Yeah. So on I equals 0, so during I equals 0, with this rfold, the prover can then use this to perform folding. So it takes the initial function f L to f, and then it utilizes rfold, similar to how Fry does it, perform the initial folding. So this will become g hat I, in this case it's 0 actually, which is the result of polyfolding. F I minus 1. So this is actually 0 in this case. K, which is 4, and R4. 0. 0. So this is the first round. So when doing this, we basically evaluate G, which will now be, so if you evaluate G hat 0 over the domain L prime, which will be actually L divided by 2, so it's half of the domain of L. In this case, you get L prime. If you evaluate G hat, which is the folded, which is F folded on L prime, you will get essentially a polynomial L that maps to F. So yeah, this is what you get in the end, the evaluation of this G hat polynomial, and the prover computes this and sends it to the verifier. So now the verifier has this. So with this done, the next step essentially is what we call the out-of-domain sampling and replying. So out-of-domain sample is essentially what happens is the verifier will actually send over this R out. This R out is a random value sampled from the finite field used, excluding what is in L prime. Hence the name out-of-domain in this case. And what the prover will do is we now then evaluate R out as the input for G. Let me just look at this. Yeah, G hat I. So in this case, if it's round 0, then I will be 0. You evaluate this on this given R out value, and then you send this over to the prover. Send this over to the verifier as well. So let me just add a few things to yeah, I think let's just make this P, and yeah, and then V sends over the R value. In the first round it's R full, in the first step, sorry. And then here it's R out. So yeah, prover takes this value taken by the given by the verifier and then sends over the evaluation. With that done, we go to shift queries. So in shift queries, again, the verifier will send over T shift queries. Okay, actually, before we go into that, let's talk a little bit about out-of-domain sampling. You can actually send more than one R out in this case for your out-of-domain sample. It's defined by a value S. In this case, it's called the out-of-domain iteration, I believe. So you can send, you will usually send more than actually one R out in this case. So let's go to shift query where the verifier again once again send the series of random numbers, R shift, over to the verifier, over to the prover, shift. And the prover will then, let me just use this. The prover will then now use this to actually construct G, which is essentially a set of R out and R shift. We can then use this to construct the next polynomial that we'll use in the next iteration of this round. So this is the first round where we actually started from F, and then through these steps, finally we actually recompute F prime, which will be essentially the folded version of F, and then we'll take this to the next round and repeat this process again. So I'll actually go through a little bit of the code so you get to see what the output looks like in practical use. So just go here. Oh, sorry. So again, we use a number of rounds as 2 to begin this. So as the first round, this is the fx that we're working with. Can you see clearly? Okay, so we started off with this very large polynomial of a degree 63, and after we fold it, this is just initial step given R fold, we actually fold it into a degree of 15. The evaluation domain reduces to Li, this is L0, and we evaluate G hat on Li and get this evaluation, this long vector, which we then commit via a Merkle commitment. This is sent over to the verifier. And the next step, we do out-of-domain sampling, which is 2 random values that we get from the verifier and evaluate into betas, which is in this case that 2 value that's evaluated that's the result of evaluation of G hat over that 2 random values. We then go into the stir messages. So this is stir messages is essentially the next step when you actually get R shift from the verifier and you use that to essentially compute your stir randomness, and then use it in the final step to define your next polynomial here. In the next final step where you actually compute F prime, we actually use a technique called degree correction that will be covered by Jade later. But this corrects the, this allows the verifier to effectively get a virtual access to the oracle. Without access to the function f, it can get access to f prime, or you can compute the evaluation of f prime during the verification step as well. So I'll pass that to Jade. Yeah.
Okay, thanks. Hello. When I implementing the stir in Python, I get my hand dirty, so I learned a lot from the code. not just the paper. So I want to share something that when I implemented it, I meet a bug, and when I fixed the bug, I learned that. So I will choose this case to introduce the wildfire introduce wildfire how to compute the folded function. Okay.
Hello, what's your topic?
It's the same topic. Same topic.
Same topic. Okay. Okay, let's see the proof. So we have the prover want to commit F0. It is equal to x. Its degree is less than 64, and I ignore the next. And this is L0 domain. L0 domain is generated by omega, and we choose the omega equals to 81, and the size is 64. So the L0 it is by this. Okay, and the prover can compete the F0 at this domain. So he will compete this. We will group his evaluations. Every error is the size of 4, and I ignore this. So we choose an index 1, 2, 15, and why we group this in the code, because this the omega 0, omega 16, they can map to omega 0, omega 4, omega power 8. This is omega 16. This is exactly the domain L004. And the next step, we fold F0. We choose a random R0 fold. We get GX. And we evaluate it on L1 to map to F. L1 is equal to. So his elements is equal to this. So the prover will also do this. He will evaluate G1 to on L1, and he will group that. I ignore the reasons. When he groups that, and the welfare, if he wants to query G1 and he index 1, 2. And this will omega 17 he will map to omega 4. This is exactly L1 4. And the next the welfare will choose two random auto-dom random. For example, R1 1 out and the R1 2 out, and choose the shift randomness. For example, this shift randomness is from the L0 4. For example, we choose this one. We choose omega 8. We choose omega 8, and the verifier, and how the verifier to compete G1 omega 8. He can if this is the first round, it is simple because when he choose this omega 8, and the prover will send the next four values f0 omega 2, and this four values the verifier will interpolate it, and for example, we interpolate it to get a polynomial px, and we evaluate it on the PR0 fold. And this we can get G1 hat omega 8. So the verifier can compete G1 hat omega 8 by himself. But this is the first step. It is simple for the verifier, but in the next step, it is not it is not directly to get this because the prover will use G1 hat to get G1 prime, and we can define the quotient set G1 is equal to R1 out. Remember, this shift randomness is from L04. L04. So next he will use the prover will compute the G hat G1 hat at this point. He will get five values, so he can interpolate it and interpolate it to get answer X. And he will define a new polynomial. It is G1 prime hat. It is equal to G1 hat X minus answer X, and the quotient divided by a vanishing polynomial. And this X minus R. This polynomial's degree. In our case, this polynomial's degree is equal to 10 because this degree is 15, and the quotient set size is 5. So this this polynomial's degree is 10, and we should do degree correction to get next polynomial to repeat this round. So we will do degree correction on G1 hat prime. So we will get if the next polynomial is F1 hat. It is a degree correction of that. He will get randomness combine. It is sent by the wildfire, and this is G1 prime hat. His degree correction is D1 minus G1. So he should, this is 5, and we can use this. I choose 0, 5. Because we choose 5 here, so we can calculate that if F1 hat its degree is become 15. So we do the degree correction and use this formula, and in the next round, we will fold this one. We'll choose another randomness to for this one and get G2x. This is the this is the next round. So f1x we get f1x is 9x squared, just like the code. And in the next round, we will fold f1 hat x to get gx. It's 14x power of 3. So this is okay. It is from L2 to F, and the L2 we will evaluation it on the L2. L2 is omega 3 times omega 4. It is a half of the L1, and for example, the size of it is 16, and we evaluate it, and we do the same thing. We group his values, so we can get 2. This is 4. And in the next round, the wildfire will choose randomness. For example, we choose shift from L14. This randomness is L14. This is exactly this one. So for example, he choose omega 4. He choose omega 4. So when he choose omega 4, the prover will send the 4 values to the wildfire, but the wildfire can only get G1 hat, the value of G1 hat, and he cannot directly get the value of F1 hat. We know that the wildfire will should check the fold is right or not. So when he gets G1 this 4, when he gets these 4 values, how can he get F1? How can he get F1 omega F1 omega 17? how can he calculate these 4 values? Because this is we want to get, but we only have this. So how can we get this? First, when we have these four values, we can calculate G1 prime hat. Because G1 hat prime is equal to G1 hat x minus answer x 1. The verifier can have the answer x. The prover can send the answer x to the verifier, and also he can calculate it by himself. And the quotient set is composed with the randomness. So this verifier also can know. This verifier can know. So when he wants to get G1 prime omega, he will equals to this. So because he have this, because the verifier have this one, this values, so he can use this to get G1 prime hat omega. So he will also get G1 7. Okay. When he gets these 4 values, and he will use this he will use this formula to get F1 hat omega, F1 hat. This when we use the geometry sum, this is also equal to when this is used geometry sum formula to get this. So he can use G1 hat omega to get F1 hat omega, and these four values. So he will use the interpolate to get a polynomial, for example, P2x, and he will evaluate it on R2 fold, and he will exactly get G2 hat omega. We choose the randomness is omega 4. He will get this one, and this is exactly computed by the verifier by himself, because the verifier should check the fold is right, so he will reduce to use this calculator to calculate the final polynomial at some randomness. We can see the sorry. So the prover when he to verify, the first is check the final polynomial degree, verify the Merkle path, and he will recompute the randomness. And the next is he will use this stir randomness. This stir randomness is exactly the R shift. And the oracle answer is I computed here. This is the oracle answer. And when he gets the oracle answer, he will interpolate these points and to get the interpolate polynomial, and he will evaluate it at the R fold and to say if it is correct. Next he will this is the folded answer, and he will also check the answer X and the shake polynomial. This shake polynomial is not shown in the paper, but it is a technique in the stir code. And this is the second round verifier. So he will also compute the folded answer by the oracle answers. And in the final, when he verifies the final polynomial, he will also compute the folded answer to get the folded answer to say if it is correct with the polynomial 7-3. We can see that the verifier, the last final polynomial is a constant polynomial. It is 7-3, so we check that it is correct. Okay, thanks.